Okay, well, hello everyone. So welcome to May Fundamentals, and I'm going to be giving a talk tonight on how far can you see, and this is going to involve also the sky conditions we have to deal with these days, which really affects how far you can see, right? And kind of going to talk about my experiences because I've been with the club a long time, nearly 20 years now. And I've got to see what's been happening with the skies, as you've been observing all these years. And kind of tell you what my experiences have been. So I guess we'll get started. So kind of 3 points that how far you can see kind of leads you to ask. One of them is why, which is kind of like why are we kind of engaged in trying to do this in the first place. And in part it is to appreciate what you're looking at, appreciate our place in the cosmos. So really distant objects like quasars, for example, don't look like much, just like faint stars, but once you realize what they are and how far the light has traveled to reach us, that makes that object a lot more interesting to seek out. Then we also have to consider when you're viewing, and that is to recognize that we've had changing conditions over the years that really affect our ability to access the skies with our scopes. And so that requires us kind of to adapt to these changing circumstances to still be able to engage with the hobby. And then when you observe, so that's another aspect, which is that, where I should say, because we have these challenges with the skies, it's good if we can expand kind of where and how often we view. So to utilize sometimes right where you live is good because you can still be engaged and have fun with the hobby, as opposed to just saving everything for like the adventure out at the dark site. So with that in mind, then we can kind of get started in earnest. So the first thing we're going to look at would be kind of the understanding our place in the cosmos. Right? So if you were to ask in the past, how far can you see? For most of human history, this was the model of the universe, that some version of this, that the Earth is at the center and everything else revolves around, with first the sun and the moon and the planets, and then at the very edge, the celestial sphere with the stars. And so it was Timothy Ferris in his book who had figured out, or cited people who had figured out, well, how large would this actually be? And when you consider like the motions that you observe and so forth, they arrived at a figure of about 50 million miles. So that's the radius of this type of universe. So if you were to ask how far can you see, the answer would be 50 million miles, right? That's it. So of course our modern understanding is that the sun itself is 93 million miles away. So we have certainly expanded our understanding of distances since that time. But what's interesting to know is human beings have been around, modern humans, they say, for roughly 300,000 years. So this model, more or less, has been for almost all of that history. That's what people in some version have understood. So it's only in the last few hundred years, as we developed technologies with telescopes and people began to take all this data that they had and look at the universe in a new way, that we understand something larger than with the Earth being the main part. So this is William Herschel. So he was a very important astronomer in the 1700s, and he was one of the first then to develop a more modern view of what the universe itself is. So he studied where all the stars were in the sky that he could observe, And then he came up with this idea that we are not the center of the universe anymore, but that as Copernicus and others began to show, and what he proposed is that the sun and the solar system are part of a rotating disk of stars. And this is more or less correct. That would be a good description of the Milky Way. So at that time, if you were to ask how far can you see, then the answer would be, well, the Milky Way, right? Whatever is in the universe is somewhere in the Milky Way, and that's as far as you can see. Herschel didn't know distances exactly. We didn't have measurements yet to the stars. He estimated that the sun to the front edge of the Milky Way, that is towards the bottom of this drawing, would be something like 50 times the distance of the sun to the bright star Sirius. So it's a serious underestimation of the size, but it was a big improvement of what we had before. So when we look at this model he has, you see kind of a dot in the center. So that dot would represent the sun and the solar system. So compared to the first model we had, now that universe would fit inside the dot at the center. So it has expanded quite a bit of where we were before. You see kind of these legs kind of to the right, and that reflected that he was seeing dust lanes in the constellation Sagittarius. So he was trying to make an accurate model of what he could see. Herschel himself had a couple other interesting ideas where he said he discovered over 2,000 different deep sky objects, which is just amazing. And he said maybe some of these that I discovered that just look like nebulae, maybe they are rotating disks of stars too, like the Milky Way, which is now what we know is actually correct. But he didn't know for sure. So in that case, the universe might actually be bigger than just this. There was another interesting idea he entertained, which was that maybe the Milky Way is the main part of the universe, and maybe some of these nebulae I discovered are just smaller rotating disks of stars that would surround the Milky Way, sort of like islands would surround a continent. And so that was a very fascinating idea, as we will see. So now we come to this, which would be more of like our current understanding of the universe. So we can kind of build on Herschel's idea of islands and continents, but now in a little different vein. So what we know now is that there are an enormous number of rotating disks of stars, an enormous number of galaxies, and they tend to collect into clusters, or what we would call superclusters of galaxies. So what I developed here was a kind of description of the universe, in part based on my observations doing the Herschel 400 program. And it's very cartoonish and simplified, but it gives us an idea of a kind of structure to the universe, in that these galaxies will coalesce into superclusters. So the universe is structured where you have areas of greater or lesser density of galaxies. So this red dot that you see there represents the local group. That would include the Milky Way, Andromeda Galaxy, Messier 33, the Pinwheel Galaxy, and others that are nearby us. So now the previous models of the universe that we saw all would fit inside the red dot. So you see again, things are expanding once more to incredible levels. So a couple other interesting things about this is just how recent this is in human history for us to have this kind of understanding of the real scope of the universe. So I remember when I was a kid, I was playing ball in the yard with my grandfather. And so when my grandfather was really young, he was born around the turn of the 19th century. At that time, the scientific consensus was the Milky Way is the universe. So Hubble hadn't even done his pioneering work yet at that time. So when my grandfather was like a young teenager, the same age I would be when I got into this hobby, it would be that red dot, right? So when we think of our understanding now, it's really within just a few generations only. That's not a lot of time in the whole scope of human history. So it would represent like 0.001% of all of human history, if you figure 300,000 years that modern humans have been around. So we've come a long way in a fairly short time in just having this different concept of the scope. So what I put here was a couple important galaxies. One is a dot we see marked 1961. So that is an individual galaxy that is the farthest galaxy in the Herschel 400 program, about 180,000 light years away. And it's a galaxy that's just kind of on its own in between the Virgo and Perseus Pisces superclusters. We see our local group itself is not in the middle of the Virgo supercluster, but is to the side, in between it and a smaller one called the Fornax supercluster. And these derive from the constellations where the great concentrations of galaxies would be visible. This model explains why 3/4 of all the very brightest galaxies in the sky will be visible just in a few constellations in the spring, which would be most of them in Virgo itself, and why another portion would be more in the southern skies, the Fornax constellation. So we are really in between these two large superclusters. So when you understand the universe in this sense, it also helps explain why galaxies line up the way they do in the sky. I have another galaxy, 7331, that's just above the red dot. That's another galaxy similar to the Milky Way, also like the Milky Way in between the two clusters. That one was very interesting because there's a direct line of sight between it. As you go red dot 7331 to the top of the page, you'll intersect the Perseus Pisces supercluster. So it means when you have that galaxy in particular in your eyepiece and you got great conditions, you can see galaxies that at first seem like they're satellite galaxies of 7331. They're right in the same field of view, but they're actually in this supercluster 6 times farther away than 7331 is, or about 300 million light years. So they're nicknamed the fleas. So I was able to see the brightest of those once at a dark observing site, my favorite dark site observing site. It's about 13th magnitude, so to see that with a small telescope is really good. And when we think then of 300 million light years, that's a pretty good distance, especially for amateur instruments. So this, what we show here, though it's just what the universe would be for modest telescopes, it still covers a very impressive amount of space. So when that light first left the flea and headed to us, then the Earth was so different you didn't even have dinosaurs yet. So if you think about it, it took so much time for that light to get here that the species that would actually be looking at it and understanding what it was didn't even exist at the time the light left. It took a long time for humans just to evolve here, why this light is traveling to us. And now the light will continue to go past us towards the Hydra Centaurus supercluster, and it will take another 250 to 300 million years till it gets there. So if we imagine there might be some aliens in a Earth-like planet on a galaxy somewhere there, so those aliens may not even exist yet. They may take millions of years yet in the future just to evolve, just as it was for humans. So this is quite an amazing scale indeed. And this is just a small corner of the universe. Now, the farthest objects that we'll talk about tonight are quasars, and they are so far that they are off the page here altogether. So just a reminder that this is hardly the whole universe, but just a small portion of it. And there'll be two targets we'll look at with the fleas in Pisces Perseus, and one more, the Coma supercluster, over on the left hand side of the page, which is also another fascinating area. So now that is kind of an idea of the scale of things, why we might seek out something far. So here I'm going to present now the problem for us to try and see things that are really far. Maybe I'll turn the light down a little, if this works. Yeah. So here is, I trained my telescope on the constellation Virgo, and at the heart of the Virgo cluster of galaxies. And that is an area that's only a couple degrees across in the sky, and it is the richest field for galaxies for small telescopes. So my first observation was made from one of the club dark sites, Caton Farm, and this was made back in, I think, 2009. So back in 2009 is when I did this. And I had a 6-inch refractor. Currently I have a 4.7-inch refractor. So they're both very equivalent, it turns out. I was able to see everything in the slightly smaller refractor as I did in the somewhat larger one, but I prefer the smaller one. It's more compact and easy to travel with. So differences we'll see here are not due to the telescope, but differences we'll see here will be due to changing conditions with the sky over time. So top was Caton Farm, 2009. Bottom is one of my favorite dark sites, which is Cross Timbers State Park in Kansas. So it's ostensibly a Bortle Class 2. It's a beautiful area to view. You get a cabin to stay in that's on a lake, and you just walk out of the cabin at night and you get these beautiful dark skies. And that's where I saw some of the most challenging objects that I've ever observed, is from that site. So back in the similar time frame, like the early 2000s, 2010s, when I was actively engaged with the Herschel 400 program, Cross Timbers was really very helpful for me, as was Caton Farm. So what was discouraging for me in this trip back in 2022 to my favorite dark site is that when I revisit Mark Heron's chain, I'm missing galaxies. The arrow will show it. So back in 2009, I could see galaxies down to 12th magnitude. So we have a range here from 9th to 12th magnitude. And I could do that even using moderate power, like 125, 135 power, because the skies were good and you could use higher power and it'd be nice, crisp views. Now going to Cross Timbers, then all these years later, some 15 years later, now there's been an obvious degradation in the sky. I'm down to just low power because higher powers are just not clean anymore. And so that also hurts your ability to get faint galaxies. And then I'm able, by struggling, to get most of what I saw before, but not everything. So that's not a good outcome to have, especially since you're not just viewing from the same site, but what is, in fact, a much better site than Caton Farm. Then I go back to Caton Farm now, and I'm happy just to see the two bright Messier galaxies that we see. And I really struggle to get the 10th magnitude galaxies. So I've seen an enormous degradation in the sky over the years that I've been viewing. So here is another example of one object, and to show how things have changed over the years. So there was a study that Dark Sky Society did where they got some empirical data So they had people out throughout the country and at different sites just counting how many stars they could see on a regular basis, and doing this over years and years. So they were able to gather together some good data. And what they found empirically now is that there's clearly been a continual slide and degradation in the number of stars visible year to year. They had cited something like a 10% drop per year in what you can see. And so then I wanted to find out, well, what does that mean in a practical sense? And so what they had said was, if you imagine someone born today, and we go out tonight and count how many stars are visible in our area, wherever that may be. Now, by the time this child born today reaches their 18th birthday, the number of stars that will be visible then, if the trend continues as it is now, will be less than half. So they said if you could count 250 relatively bright stars tonight, you'll only be able to count about 100 18 years from now. So we can imagine like that's a bad decline. So here we have a view of the Eskimo Nebula, and this is one that I saw 18 years ago. And this I saw from, I used to live in Lombard at that time, and that's going to have skies very similar to Naperville, Plainfield, the western suburbs, right? And so very inferior to Caton Farm and our other club dark sites, but yet you would get nights like this one where I could use extremely high power. You see 400 power with a 6-inch scope. So that is power that would exceed what people tell you is the normal useful magnification you can have, and by a wide margin. But yet you would have conditions so good that you could use this ridiculously high power and get really clean views. As a consequence of that, I could see the nebula. I could see a 10.5 magnitude central star in that nebula. And that's hard to do because the nebula is trying to hide the star, right? Make it harder to see than if it was just on its own. And then I could see 2 field stars above it, a bright 8th magnitude field star, though that's pretty easy, but a 13th magnitude field star as well. So there's one amateur astronomer who called this the Eskimo's wife and child. And I like that phrase a lot. So I could see both the wife and child of the Eskimo. And 13th magnitude is as faint as I've been able to do with my small refractors. So I'm able to get the limit, and get the limit like here, right? It would be like going out in Naperville, right? Not a dark site, high power. You can get as faint as you could get 18 years ago. And then not only are you getting that, but then when you put a filter on, you can get beautiful structure of the Eskimo. You can see these shells that it's made of. So this is like marvelous stuff you can see, right, when the skies let you. So what's happened since? So on the top left, we see another view of the Eskimo. This was again from Cross Timbers in 2022. And it's like, oh my goodness, what a difference. So now I can just see the nebula. I can't resolve the central star. It's washed in. I can't see the 13th magnitude star anymore. So this is really bad. And then on the right is a view I have of the Eskimo that I made in February of this year from where I currently live, which is downtown Chicago, right? So at first blush, this looks really bad because, the current views we have of the Eskimo aren't, at the dark side, aren't better than downtown Chicago right now. But there is a silver lining in this. So the first thing is, even what am I doing trying to even try this from downtown Chicago in the first place, right? So one thing I learned was that in spite of the bad light pollution, I could still do my hobby. And that was really nice to learn. And I tried the Eskimo for several years. I moved back to the city in 2021, and I would try and not catch the Eskimo. And then I did now in February. And so just to see it was very encouraging. Like, wow, I could get it after all. And then what it was teaching me is that this degrading that we have, while very real, isn't as horrible as at first it was looking to me, like irreversible and you can never go back. It's like there is hope that at least we get some nights again where you can get clear skies enough to, to be able to get a decent view. It's just not going to be nearly as often and regular as it used to be in the past. So then continuing here, another thing I just told you was, the projections are we're going to see less than half as many stars in the future as we do now. So what would the future of our hobby be? Well, I think if we live out here in the western suburbs or go to our club dark sites, it's just going to get worse and worse, right? But would it ever get as bad as downtown Chicago? That's an interesting question. But so here I'm able to view from the worst place any club member has right now and still do some astronomy. So there, even though things will continue to degrade, there's still hope, right? That you can go out and enjoy this thing. So what I did then, or started to develop ideas of, is if you want to see as far as you can see, you need to first select different types of objects. So it broadens your ability to have fun with this and then try and see things in spite of the challenges. So the galaxies would be on the bottom right, the normal thing you'd think of for the farthest you can see. So I did include that, but I also included other types of objects, tried to see the farthest star cluster or globular cluster or nebula. So that way you can have other challenges. Star clusters in particular are very resilient to light pollution because they're point sources. So it gives you a chance to still be engaged with this even though the conditions themselves get more and more adverse. So the cluster on the top left there is called the Phi-Cas or ET cluster. So it has a very distinctive form, like two bright eyes and a guy with his arms outstretched. So it's very fun to look at. I had done a fundamentals a few months ago about star clusters. At that time I showed a drawing I made of the same one 20 years ago from Lombard. And now it's nice I can have a modern one that I can show that was made just a few months ago. And when I compare this to what I saw before, I'm not missing anything with this particular cluster, so that's nice. So this one has stars bright enough that it's been resilient through the light pollution. Other clusters, no, if they have fainter stars that make them really nice, that's lost. But there are a lot of resilient clusters out there still. So that's some good news. So I've been able to see that. I've been able to see a globular cluster like M3 that's about 30,000 light years away. So that's not bad for the city. And then that's the Orion Nebula at the bottom left. So this is something I've been viewing for years and years with this hobby. So here what I get is a severely reduced image of the Orion Nebula. But in a perverse way, it helped highlight things by, whether I liked it or not, wiping out a good portion of the nebula. And I could see then the heart of the nebula. It highlighted what's called the Huygens Center, which was discovered by Christian Huygens in the 1600s. That's about all he could see with his crude telescope as well. And then you have the trapezium, these four stars that are right at the center of the nebula that were formed out of the material in the nebula. And they're very young, hot stars, and their light is now blasting away and removing some of the nebulous material for visual viewers, and it creates what they call the keyhole. So you can see all these interesting details in the nebula even, in spite of the most adverse conditions, right? You can imagine with light pollution. So where I'm viewing this from is a balcony on a high-rise on Randolph Street, looking towards the Aon Center, 2 blocks away. It's a 1,100-foot tall skyscraper, lit up, right? 2 blocks from me. And still, I can do this stuff. So it's like there's hope then for the western suburbs, right? Even if things decline. And then lastly is that's the Andromeda Galaxy. So I even got to see a galaxy. So that's the farthest I've seen from downtown Chicago, 2 million light years away. So that's kind of cool. Now, of course, I've seen the Andromeda Galaxy with my naked eye at the dark sites, but I'll take it. When I've seen Andromeda from dark sites, it's huge. I've made drawings where it's 1.5 degrees wide. That's 3 full moons side by side. So here, it's more like a crater on the moon. I'm just seeing the very core and nothing else. But yet I had a lot of fun, which is a big part of the hobby, just trying to track it down. So even though it's the worst view I've ever had of it, it was one of the most fun times I had, just trying to see if I could catch it. So here's if we take then 4 groups of objects to try and find the farthest, here is a kind of description of how they relate to the sun, right? So this is another model I created when doing the Herschel 400 program. I would get data for about 100 star clusters that you had to observe. I would plot where they were based on the NASA database in terms of direction and distance from the sun. And I realized some of them will kind of be close together in groups. So there were about 24 groups all around the sun where these objects were. So what this taught me is this is actually, when we are observing with our telescopes, all that we can reach if we're looking for something in the Milky Way. And this will be true even with large telescopes, because all these things are in the plane of the Milky Way, and there's a lot of material in the plane of the Milky Way, and it blocks visual telescopes from seeing too far. So the way we really know the structure of the Milky Way is we have to go outside of visual wavelengths to radio telescopes, or now orbiting telescopes with infrared. And then we can go beyond that. But this circle about 10,000 light years radius is what we're really looking at when we're looking at anything in the Milky Way in the sky. So that surprised me, because before I had started this, I thought they're just everywhere in the Milky Way, right? But no, they're really more concentrated just around the sun. We can see where the sun is. It's about halfway roughly between the core and the edge, and kind of making a cartoonish sketch of the core, the bar, and then some of these spiral arms off it. So the farthest regular clusters we could see would be down towards the bottom of the page. That's the Perseus arm. What would be groups like 11 and 8 are ones I'm going to highlight here tonight. And then we have this interesting one that's at the very bottom of the page. That is a star cluster that is at the outer arm of the Milky Way, some 17,000 light years away, so outside of this normal radius. So that's a lot of fun to seek out, because if you see that, then you're looking at something that's actually towards the edge, the very edge of our Milky Way, not an easy thing to catch. So here are my sketches of that. So you can see they were made a while ago, back in 2006. and 2011. So the first one is a beautiful star cluster in Perseus. So that would be at the edge of the 10,000 light year range. So not bad. This was made from Lombard, so something you could duplicate easily and easily today from anywhere here in the western suburbs. And then the one on the right, that's that distant cluster in the outer arm of the Milky Way. That one is about 11.5 magnitude, so it's very faint. So at that time I could see it from Caton Farm. I don't think I could do that today. This is one you probably have to go to a better dark site, maybe one of our club dark sites on a really good night. You could catch it, so it's more of a challenge, but worth it if you can get it. Next group then was the globular clusters. So here I have a sketch, again, like I did for the open clusters, to show how they relate to the sun. So now we see the Milky Way is shrunk down. There's a hub at the center around the nucleus of the Milky Way where about half the globular clusters reside, and then the other half are spread out all around the galaxy. And they're not in the plane of the Milky Way, because the Milky Way is more like a plate, a dinner plate, when you see it sideways. And so because they're above or below the plane, then we can see them easier. There isn't material getting in the way, blocking our view. So the typical Messier globular cluster will be about 25,000 light years, and it's going to be kind of still within the Milky Way itself. We see two interesting clusters out to the left. One of them is NGC 6229 and the other NGC 7006. And those are among the farthest that you could catch, that I was able to catch at least from here, western suburbs. So the first one is in the constellation Hercules, like M13, but it is 4 times farther than M13. So if you can catch that one, you would be seeing something 100,000 light years away, and that's pretty good. And then 7006 is even farther, 135,000 light years. But the very furthest we would have here would be way at the bottom of the page, and that is NGC 2419. And that one they got the name Intergalactic Wanderer. When it was first discovered, astronomers thought it's so far away that it doesn't even belong to the Milky Way. But later studies have confirmed, no, it does still orbit the Milky Way, still is gravitationally bound, but extremely far away. So this is well over 200,000 light years away. I think 275,000 light years away. So that would be the farthest Milky Way globular cluster accessible for moderate telescopes. And so here again are my drawings of it. So I was able to see the first two from the western suburbs. Right? Now I don't know though if we could do that today, because they are kind of dim, getting to 10th magnitude or so. So the degrading of the sky may force us to have to go to one of the club dark sites now to try and catch this. You can see beautiful stars that are field stars around these, especially the first one, 6229, makes it look sort of like an insect sort of with legs at the bottom. And then I went to the site of the Iowa Star Party, so a very dark site, Coon Rapids, Iowa, and it was there where I was able to catch the Intergalactic Wanderer, which also goes by Caldwell 25. It's in the Caldwell catalog as well. So that one is really beautiful to see. It's not as concentrated as the other two because of the distance. So it's this really soft glow, but a lot of fun to catch if you can. So now if you do imaging, then what you could do is image these things. You could certainly image them from here, and you might even be able to resolve some of the brighter stars within them. So that's the advantage of electronics and imaging. So now we have the third one, emission nebulae, like the Orion Nebula. So here on the left is a view again from western suburbs, but made a long time ago, back in 2005. This is M16. So this one is about 4 times farther than the Orion Nebula from us. And so this one was made famous. You see a star I marked P. It's part of a cluster of stars that are associated with the nebula, so many of them born out of the nebula. So star P is interesting because that is the area where the Hubble telescope imaged the pillars of creation. And so if you do imaging, you actually have the ability, with how good technology is today, to capture the pillars yourself. Not to the degree the Hubble did, but you could still capture them. So that would be a fun thing to try. So for me, visually, I can just see the star, the area where it's at, and the nebula. So what's the farthest nebula you can see? That would be an extragalactic nebula. So that's really cool. So when I was out in Caton Farm, I was able to get a great night where I could really resolve M33, the Triangulum Galaxy. It's part of the local group, and I could see the core, I could see the spiral arms coming out, and then this bright knob at the northern end of one of the spiral arms. And that bright knob is a nebula much like M16 or the Orion Nebula, just much larger, so we're actually able to see it from this great distance. That nebula, which is NGC 604, also responds to filters, like nebular filters, like an oxygen 3 filter, just as M16 or the Orion Nebula does. And that's really cool when you're looking at a galaxy and seeing this thing respond. It's much more subtle because of the distance, but it's noticeable. So to me, this was really cool to be able to see a nebula in another galaxy. And so that's another reason you like to see how far can you see, because what it brings to you is how these galaxies really are other island universes like our Milky Way. Our Milky Way has a core and spiral arms. Now we can see a core and spiral arms in M33. Our Milky Way has nebulae that form stars, and now we can see a nebulae that forms stars in that galaxy as well. So it's a cool kind of aesthetic thing to realize when you're looking at it. Yeah, Tom.
Could you point to some of the things that you've captured there in your drawing, like the attributes?
Okay.
I can see some of them, like I can see the M16, for example, but like, what do you like to capture when you sketch?
So when I sketch, I want the field stars, and I want to get them as accurate as I can. So like, for example, the star P. And then I want to capture where the nebula is with respect to the field stars. So you're kind of training your eye to pick out detail. And when you do that, then you can see more detail, right? Because you're trying not to overlook things. And making a sketch helps you like sharpen your eye and your vision. So here I could see kind of a forked appearance, at least at that time, for M16. And then with M33, there is an important group of stars that you'll see to the left of the nebulae itself. And those are important field stars because they kind of point you to where the nebula is. So it helps train your, lead your eye to the right part so you could see where the nebula is. And so I would try and make an accurate sketch of those field stars as well, because then that helps guide your eye to where they are. So again, imaging would be really cool, with this thing too. I can only imagine what some of our group members could do with this.
You capture the object, and then let's see, like Lombard, I think bottom left corner.
Yeah.
What do you have in the bottom right corner of each? Like, is it
so this was Caton Farm. Caton Farm was where I was able to make the view of the NGC 604. So it would be too challenging for western suburbs. Another way you know it's too challenging is because M33 itself is degraded in western suburbs. All you get is the core at best, and it has a very low surface brightness. And so this is another way you can tell, can you get these objects or not? And it's going to be if you are not able to resolve like the host galaxy, you're not going to get the nebula, right? So getting great resolution of the galaxy tells you you now got a shot at this more challenging thing. And we'll see that come up with other things like the quasars too, in terms of the field stars. You better get the faint field stars before you have a shot at getting the quasar, right? That's how it works. So you can tell, like, is this going to be your night or not to capture this kind of thing. So then how far can you see for an emission nebula? Over 2.5 million light years. So that's pretty cool. This is again with modest telescopes, right? All you need is the sky to cooperate. So the last group there was galaxies. So here was my view from cross timbers. Both were made at cross timbers. The one at the left was in 2017. That was when I observed NGC 7331 that I had highlighted with the map, the universe map earlier. And then there's one of the fleas, the brightest flea, NGC 7335, over to the left. There are 4 field stars that make kind of a square. They get down to 13th magnitude, again, as faint as my small telescope will go. So then when I was seeing the 13th magnitude stars and seeing them easily, I knew, like, this was a good night for viewing. You can get that reinforced by the great detail in 7331, where you see the bright core, then it's a little less bright, but still really bright, moving away from the core, and then fades even more as we get to the edge of the outer arms, a kind of sharp edge on the right-hand side, which belies the presence of a dust lane. So this is like really nice definition for a very small telescope. And so when the night is that good, then you have a shot at seeing really far. So this galaxy, the flea, is 13th magnitude, but not a point source 13th magnitude, an extended object 13th magnitude, lower surface brightness, because this light is spread out. So for you to catch it, you need really great conditions, but really rewarding when you get it. So there I'm seeing 300 million plus light years away, right? With the scope I can put in a suitcase, literally do, and fly on an airplane with it, right? So at that point, that was the best I did with my small scope. And then as I showed you the earlier drawings, then I would go back to cross timbers in 2022, and it's like, it's looking bad. And I was thinking, I'll never have a night like this again, right? And then came this year, I went out to cross timbers in March. And I was so happy, like, my goodness, I had one of these, actually 3 nights in a row of just great skies once again. So now it's telling me, like, you can't expect these regularly like it used to be, but they're not entirely gone. And so what I was able to do this time around was capture this object, Caldwell 35, or NGC 4889. And this is a galaxy in the Coma supercluster, and also some 300 million light years away. And this was something I always wanted to catch for years and was always denied. And so when I got to see this now in March, it was kind of emotional for me. I'm like, wow, I finally got to see this thing, right, after all these years and always trying to see it. So I would like to go back to this area. I may need an even better site, maybe higher elevation, because this area, the Coma cluster, is like the Virgo cluster. So if you can see it well, you can see like a half dozen or more galaxies in your scope in the same field of view at the same time. It's very impressive, but these are all so far away So for this night, like, I'll take it, at least I got to see the brightest member of this cluster and capture it. So that's the overall lesson here, is that it's harder to get nights like this, but thankfully they're not totally gone forever. There's still times we can get where we can still see really far. And so the last are quasars. So these are the furthest that we can see with modest telescopes, the furthest objects. And thankfully here, I'm not showing you drawings from 20 years ago. It's back in March of this year. So I got my record farthest thing now in modern times. That's encouraging, right? As opposed to just you could only do it in the past. So we have the object on the left. That's Markarian 421. So here we see this astronomer Markarian again. We had seen the Markarian chain, could be named after him because he had discovered common motion with those galaxies. And he also developed a catalog of galaxies with bright nucleuses. And so that's how this particular object wound up in his catalog. So what a quasar is a galaxy. But it's a galaxy with a very active nucleus. And what we mean by that is it has a black hole at the center, like almost all galaxies do. However, it's in a unique situation where there is, for a variety of reasons, a lot of material around this black hole. They tend to be objects that that are very distant from us because they were very active when the universe was younger. That's when more material, for a variety of reasons, was available in galaxies to coalesce around black holes. So what happens is that the black hole will be attracting a lot of material, a lot more than like what's happening now at the Milky Way, for example. We have a black hole, but it's very quiet compared to these. But quasar black holes have a lot of material to work with. They're pulling them in. And when they pull them in, there is an enormous, like, humanly not comprehensible amount of energy and light being released. And that's why they can be seen over extraordinary distances. And so what I was told was, if you take our sun, for example, let's say we take a star that's an exact twin of our sun, and we put it 10 parsecs away. So that's a little over 30 light years away. If you were to go out at night and look at that star, it would be 4.8 magnitude, so nearly fifth magnitude. These days, that's as faint as you get with the eye. You know, the typical, they say, is 6, but practically now it's 5, right? And so that means that the sun at 10 parsecs is going to be like among the faintest stars you could see with your naked eye these days, right? So now if you take a quasar and put it at the same distance, now night sky is gone, and you've got an object that's shining, depending on the quasar, even brighter than our sun, as we see it now, minus 27th magnitude, right? So it tells you the difference in energy and brightness between a quasar and an ordinary star. So also what's happening, because material is falling into this thing, is eating, as they put it. So when it's really actively eating, it's really bright. When some of the material has been digested and there is a pause, then it dims, right? So these are variable. So this particular one, 421, will vary 2 magnitudes from 12th to 14th magnitude. So here I was lucky this night because it was at the brighter end. If it's 14th magnitude, I don't see it, right? But it had been snacking 400 million years ago, and then I just happened to get the right moment when it had had a good meal and got to see it, and see it very clearly with direct vision. So that was cool. So now the one on the right, that is a quasar designated 3C273. And that is generally considered the farthest object for modest telescopes. And I think that's a fair description. There are some that are a little fainter, a little further. They get harder to see because they tend to be lower in the sky, and all these little things add up. So they can be accessed with amateur telescopes, but you start to need larger ones to do so. So this one, a fair statement, the farthest for a modest telescope. So this I got to see when it was directly overhead. This is also something I've looked for years at cross timbers with no luck. And then here, I finally had the right conditions. So what you do for these things is you find the right spot. I do it by star hopping. There are other ways you can do it. Then you know you're in the right spot because you'll have a sky chart. And you're going to match the stars you are seeing, the field stars, with your sky chart. And so they better look the same. And if they don't, then you know you're not in the right area. So you have a very bright star to begin with, and then you have kind of a triangle of stars to the right after that. So your quasar is going to be kind of in the one side of that triangle of fainter stars. So the two stars on the left side, the two field stars, are at magnitudes 12.7. So nearly to my 13th magnitude limit. So then like if I can't see those stars, I'm not going to be seeing the quasar, right? But this night, I did see those stars. That was cool. So I knew, okay, I got a real chance at doing this. And then, sure enough, you have to spend a little time with it, but then this 13th magnitude quasar kind of appears. So it's right at the limit of what my scope can do, but you spend a little time and, it becomes very definite that, like, there it is, you're seeing it. So once I did this, I became a member of what they call the Billion Light Year Club. Right? So those are for observers of quasars. So the light from this object is so far away, it took 2.5 billion years to reach us. So to put this in perspective, when that light left the quasar, the Earth was about half the age it is now. And what was the Earth like at that time? Humans could not live on the Earth at that time. First, there was no food, because the most advanced life at that time on the Earth was bacteria, not even multicellular yet. And most of the bacteria were just in the coastal areas of a landmass that is our continents, but put together, unrecognizable in form from where the continents are today. So just along some coastal areas, you had the majority of the bacteria. When you went onto the land at that time, it would be like walking on the surface of Mars. There would be nothing but rocks and sand. There would be no life whatsoever, at least no macroscopic life whatsoever, so no food to eat. Then on top of it, these bacteria eventually through time would induce oxygen into the atmosphere, but back then that process was very much in its infancy, so you had hardly any oxygen in the Earth's atmosphere at that time. So you couldn't breathe and you couldn't eat. So if you were to go back and visit the Earth at that time, you'd be like going to Mars. You have to bring your own air, your own food, and even deal with harsh radiation. We didn't have an ozone layer yet. So very Mars-like, is what our world was back then. So this drama, when the Earth is that young, is taking place in a distant galaxy, this immense heat and light being generated, and then it's just moving across space, and it takes all this time to reach us that, the Earth itself has been completely transformed, and now you've got humans on the scene who are able to see this and appreciate it. So to me, that was really cool. So lastly is open challenges. So the first one for me is a globular cluster called G1. So I've seen an extragalactic nebula, so you also have a chance to see an extragalactic globular. So this is a globular that belongs to the Andromeda galaxy. So I tried for it, and at the top you can see what I outlined, like a circular area. That's where it would be. I saw two 13th magnitude field stars near it. So again, you have kind of a triangular form that directs your eye where to look. But this globular is 13.8 magnitude, so it's just beyond the reach of my scope. I tried, but couldn't quite pull it in. Maybe I could get it if I went to an extraordinary site, like 7,000 feet above sea level or more, and had an extraordinary night. But probably I'm thinking I may need a bigger telescope. And then the last one is another quasar. So it has an unusual name, like PG 1634 plus 706. Not even sure how they come up with these names. But this is a very interesting one. It's in the constellation Draco, and it's not far from the Little Dipper. And so I star hop to the area from the Little Dipper, and I get these two 8th magnitude stars in the eyepiece field of view. Then I know I'm in the right spot. And there is a square asterism of stars that's super convenient, because each star, as you move clockwise, is 1 magnitude lower than the last. So the stars go 11, 12, 13, 14th magnitude in the clockwise direction. So if you're able to see all 4 stars in the square, that is, get to 14th magnitude, then you know you have a shot at the quasar. So my first attempt was in Wilton, Wisconsin. That's not far from Wildcat State Park in Wisconsin. Pretty good skies over there. And that evening I could only get, though, to 12th magnitude from that location. I tried again across Timbers a couple months ago. Yeah, I could get the 13th magnitude. That's about it. All right? So still a little bit beyond my reach. The quasar itself is about 14.3 magnitude. So again, I may just need a little bigger telescope. Why that one would be cool to see if you can, or you can image it, I think. I've been told that even without having precise tracking, people could get stars to 15th magnitude imaging. I don't image, so I don't know that's true for a fact, but that's what I've read. So it means you could get this quasar even without needing very precise tracking if you try imaging. So if you are able to capture it, you would see something so far away, 8 billion light years away. It means you're looking at something that is the light took so long to get to us, the Earth itself didn't exist when the light left. All right, now that's something. The ground you're standing on didn't exist when that light left. And because now expansion of the universe gets into play, it's now 12 billion light years from us because of the expansion of the universe. When the light left, only 8 billion light years away, right? So to see something like a part of the universe glowing that happened before our Earth existed, I think that'd be really phenomenal to see. So maybe one day I can, or maybe one of you could see it with a bigger scope or image it. All right, so that's my talk for today. So any questions?